the big picture is that we're building to this method, the Gram-Schmidt orthogonalization method, that's going to allow us to use an existing basis. So you're given an existing basis, and then you're going to create an orthonormal basis. And remember, an orthonormal basis is a basis where all the vectors are perpendicular to each other and length 1, perpendicular length 1. These concepts will help us to develop a method for calculating the least squares method. So given a vector y and a subspace w in Rn, there is a vector y hat in W such that y hat is the unique vector in W for which y minus y hat is orthogonal to W, and y hat is the unique vector in W closest to y. We've drawn this picture a couple of times, but let's draw it again. So imagine that you have some subspace, maybe we'll use a line today. So this is our subspace W. And then we have some vector that's not on W. We'll call it Y. So then this vector here would be our Y hat. It's the projection of Y onto W. And then we'll call the part that's left, we're going to call that Z. And the formula for Z is that it's equal to Y minus Y hat. Okay. Woohoo. So let's see what's going on here. We're saying that this Y hat vector is the unique vector in W closest to Y. And you should be able to see that like graphically because you got the 90-degree angle, so it should make intuitive sense. But we're talking about closest to Y. This could be in not just 2 dimensions, but 3 dimensions or 5 dimensions or 100 dimensions. So the idea of close isn't always as obvious as it is in this picture. And then Y hat is again the unique vector for which Y minus Y hat, this would be our Z vector, is orthogonal to W. So let's look at this theorem. So theorem 8, the orthogonal decomposition theorem. So if we let W be a subspace of Rn, then each Y in Rn can be written uniquely in the form Y equals Y hat plus Z. I guess let me keep the picture up. So notice that the Y hat, again, this is the part in W, and then we have the Z part, and that's the part in W perp. Okay. So where Y hat is in W and Z is in W perp. In fact, if U1 to UP is any orthogonal basis of W, then we even have a formula for our Y hat. So our Y hat is equal to Y dot U1 over U1 dot U1 times U1. So there's our weightings or our coordinates with respect to the orthogonal basis. And then our formula for finding Z is just take the original Y and subtract out the part that's in W. So let's do an example of this. So if we let W equal the span of U1, U2, we want to write Y as the sum of a vector in W and a vector orthogonal to W. So vector in W, this means Y hat. Vector orthogonal to W, this means Z. So we've got our formula. So it's going to be equal to Y dot U1 over U1 dot U1 times U1 plus Y dot U2 dot U2 We were playing U2 music before, so this should feel comfortable to you. And we've got that our z vector is equal to the y vector minus the y hat vector. So there's our formulas. So we got a whole bunch of dot products to do. Yeah, I guess we just do them. So y dot u1. So somebody can you guys find me? Maybe I'll highlight them one at a time. Y dot u1. Okay, I got 0 from Felix, Evan, Twee, Megumi, and Gerald. So nice. Got a 0 here. How about u1 dot u1? I've got a little bit of multiple choice, but mostly 14s. And so I think I'll go with the majority on this one and call it 14. And then, yeah, it shouldn't matter from Evan because you have the 0 in the numerator. And then next we've got the y dot u2. And I've got 28 from Ben, Ryan, Abed, Twee, Gerline, Richard. And maybe let's do an orange one, u2.u2. I got a 42 from Abed and Juan and Hui. Okay. So all this stuff is going to simplify. Hey. To, looks like, so 28 over 42 would be what, 4 over 6 or 2/3, I think. So this is going to be 10/3, 1/3, or 2/3, and 8/3. Yep, thanks, Abe. So that gives me my y hat vector. So this is the one in the space. And so then we also need to find our z vector. So our z vector is going to equal the y vector, which was 1, 3, 5, minus all that garbage. Which is a funny way of writing, what do we have, negative 7/3. 7/3 and 7/3. So far, so good. So far, thanks, Croy. That's touching. No, it's just amazing. So then one last little bit. Let's go back to the original question. And so the original question said, write y as the sum of a vector in W and a vector orthogonal to W. So we need to just write our answer in a specific way. And so the last thing we have here is we want to write z, not z, y. So we've got our y is equal to the green vector 10/3, 2/3, 8/3, plus, I think the other one was purple, minus 7/3, 7/3, 7/3. Something like that. So let's remind ourselves of what this means in picture form. So in this picture, our y vector would be right here. So there's your y vector. And your green y hat vector would be here. And your purple z vector would be there. And so you'll notice that there is, here you've got the projection of the y vector on the first component, and there in red you have the projection of the vector onto the second component, like in the u1 direction and the u2 direction. What's the angle in the picture between the green and the purple vectors? What's the angle between the green and the purple vectors? Yeah, from Ben and Gerald and Hui and Mahi and so many others, they're perpendicular to each other. So I hope you can see that this y point, or like that the green y hat point is as close as y can ever get to the space W. Yep, we broke our vectors into components. And so this next theorem kind of gets at this idea of closeness. So it says, let W be a subspace in Rn, let Y be any vector in Rn, sort of like the one above it. And let Y hat, that's our green vectors, be the orthogonal projection of Y into W. So then that Y hat is the closest point in W to Y. So in that sense, we're saying that your Y hat here on the left, you have the distance between Y and Y hat. That's how you want to think about it. Think about it as a magnitude or a norm or a length, or in this case, a distance, that the distance between Y and Y hat is less than the distance between Y and any other vector that's in that space. In 2 dimensions and 3 dimensions, this should be intuitive because the Y and the Y hat are just 90, like it's a projection. And so you've got that 90-degree angle. So continuing to build on the same thought, in our last example, we said that 10/3, 2/3, 8/3 was our y hat, and that it was the closest point in W, or the closest point in W. W was equal to the span of U1 and U2 to the point Y. And so if we just want to find the distance from Y to W, this is just the norm of Y minus Y hat. And we have a special name for Y minus Y hat. What's our other name for Y minus Y hat? Yeah, from Hui and Gerline and Abe and Gerald and Felix, this is just our Z vector. So if we want to know the distance, it's just going to be the magnitude of the Z vector, which would be, I don't know if you remember that Z, but that was the negative 7/3, 7/3, 7/3. So this is going to be square root of 49 over 9 plus 49 over 9 plus 49 over 9, which is something like 7√3/3. Back in the picture, this picture isn't a perfect match to this question, but back in the picture, how would I visualize this 7√3/3? Like, where does that show up in the picture? Yeah, it's the length of Z. So you can imagine trying to find this length here. And that length would be the 7√3/3. Thank you, Ben, Felix, and Abe. Questions? Let's look at these practice problems. At least let's look at the first one, maybe crunch a little bit on the second one. We're not going to do them in their entirety, but we could at least talk about them a little bit. So in the first one, I have U1 and U2 and Y given, and W is again the span of U1 and U2. And I want to use the fact that U1 and U2 are orthogonal to compute the projection of Y onto W. So my question is, the projection of Y onto W, what's our other name for that? Like, that's a complicated thing. We've got a new name for that. What is it? Yeah, from Gerline and from Megumi, this is our Y hat. Yep, Y hat. So this question is basically asking us to do the same thing as before. Okay. And then second question, it says U1 and U2 are orthogonal. How do I verify that vectors are orthogonal? So I'd use their dot product and show that it's equal to 0. Thanks, Ryan, Ben, Twee, Felix, Hui. So and in this case, they said use the fact, so you don't need to verify it, but I just want to remind you of what you would need to do if they hadn't told you, if they hadn't let you assume that they were orthogonal. So that's what's cool in the first practice question problem. And let's look at the second practice problem. So it says, let W be a subspace spanned by the U's, and write Y as the sum of a vector in W and a vector orthogonal to W. So the difference between this question and the example that we worked all the way through is that now we now have 3 vectors, U1, U2, U3. U3 is a cover band for U2, in case you're wondering. And then we have vectors that live in R4. So it's basically, we've just added a little bit more dimension. Otherwise, it's not the same, or otherwise it's just the same. And so let's again remind ourselves of the formula. So our formula is that y hat would be equal to y dot u1 over u1 dot u1 times u1 plus y dot u2 u2 dot u2 u2 plus y dot u3 over u3 dot u3 times u3 . Something like that. And so this gives me my vector in W. That's this one right here. And then we've got to find our vector orthogonal to W. So that would be our Z vector, which would be equal to Y minus Y hat. And then the question asks us to write Y as the sum. And so at the end of the day, we're going to have the conclusion that Y is equal to Y hat plus Z. So I haven't worked through the details, but that should be enough for you to see that this question is the same as the previous. You just kind of got to do a lot of crunching. So a couple of questions about this. So the first question is, what if Y was already in W? How will that change things or influence things? Yeah, from Gerald, that would mean Z is 0. That would mean Z is 0, that basically there is no error in the approximation. No error. And then Ahmed said that you'd also have that Y is equal to Y hat. Yeah, so good. So that's one question. Second question is, second question is two. Are there any special U1s, U2s, U3s that would simplify this formula? You might say, which formula are we talking about? The formula that I'm talking about is this formula right here. And from Ben, we've got that unit vectors would be really nice. Why are unit vectors so good? From Ben, 1 is an amazing number. I love it. It's a great way of putting it. So think about it here. If we had unit vectors, what's going to happen to u1.u1 and u2.u2 and u3.u3? Not so much a lot of zeros as you'll get a lot of ones. All those denominators are going to be 1. If you happen to have y be perpendicular to, y be perpendicular to u1 or u2 or u3, that would be nice, but you don't have very much control over what y you're given, right? But what we do have control over is the basis we're working with, and it's pretty easy to turn things into unit vectors. Like, for example, what would we need to do if we wanted to take, say we wanted to take that u3 vector and turn it into a unit vector? What would I need to do? Yeah, I would need to just divide by its magnitude. I think it's a square root of 3. And so I divide all those terms by square root of 3, and suddenly I'd have a unit vector, and everything would be hunky-dory. So those were a couple of questions that I hope help you understand the nuance of this formula and this method. Questions from you before we start talking about this Gram-Schmidt orthogonalization method? Very good. So let me outline what I'm going to do here in this section. So in example 3, I'm going to do the Gram-Schmidt process. And then in example 4, I'm going to do the Gram-Schmidt process. And then on the next page, I'm going to say, here's the formula for what we just did. So sometimes some students like to see it happen before the formula. Other students like to see the formula before the example. So if you want to know what's going on, you can look ahead at the next page in the notes. That makes sense? So here's the deal, that we have this W, this subspace. It's made up of the span of the vector x1 and x2. And let's just take a moment and verify, what is x1 dotted with x2? I got some 30s out there. And what's really important about 30? Yeah, from Felix. 30 is, after careful analysis, it's not 0, right? So this is not an orthogonal basis for W. But we like orthogonal bases. So it's like we have a basis. We like orthogonal basis. Is there any way of using this basis that we're given to construct an orthogonal basis? Good news, the answer is yes. Okay. So we are going to construct an orthogonal basis for W. This is what our goal is. We need a name for this instructional, or for this orthogonal basis. We got to name these vectors. So we're going to call these vectors v1, and v2. So x1 and x2 are a basis, but they're not orthogonal. v1 and v2 are a basis, but now they are orthogonal. So they're going to be an orthogonal basis. All right. So the first entry in our orthogonal basis is really easy to find. The formula for v1 is equal to x1. You just take the old vector and copy it over. Super easy. To find the second vector, we need to find the part of x2 that's perpendicular to x1. So let me write it this way. It's going to be x2, one color. It's going to be x2, and then we've got to take away the projection of x2 onto x1. Projection of x2 onto x1. That's kind of a funky way of writing things. We actually have another name for that in this class. What are we calling that? That is our x2 hat. Yeah. Okay. So good news, we now have a formula for v2. So v2 is going to be x2 minus x2 hat. That would be x2 dotted with v1 over v1 dot v1 times v1. This might look really strange. You might say, wait a second, where did that come from? But you might remember this formula as something like, you might remember the y dot u1 over u1 dot u1 times u1. Ahmed asked, if we started dealing with multiple projections of the same vector, would we have to go back to the projection notation? Nope, we're going to try to avoid that projection notation as much as possible. And so I wrote it here, but I'll try to write it as little as possible from here going forward. So projection notation is awkward. Like, it's clear, but it's hard to work with. So if you think about this formula right here from the previous section, it's basically analogous to that formula there. And so this would be like saying your z vector is just going to be this one minus that one. So let's actually do it and see how it all works. So we're saying that x1 or v1 is equal to x1, 3, 0, negative 1. And we're saying that v2 is equal to x2, 8, 5, negative 6. minus, and then we're going to have a fraction times v1, which is the 3, 0, negative 1. What is the x2 minus v1? What's my numerator? What's my denominator here? I've got from Felix and from Andrew and from Juan, I've got 30 over 10, which is a nice way of writing 3. So 8 minus 9 is minus 1. 5 minus 0 is 5. Negative 6 plus 3 is negative 3. Yep. Okay. Let's look at these two vectors. What is the dot product of v1 and v2? So it equals 0. Yay, they're orthogonal. Not only are they orthogonal, notice they are a linear combination of the vectors that we started with. So by construction, these two vectors are a orthogonal basis for that same space. So we started with W equals a span of x1, x2. There was just any basis, and we used the any basis that we were given to construct an orthogonal Cyclops basis for W. I'd like to begin by looking back at this example 3 that we finished yesterday and remind you of the big picture. So here's what we did big picture wise yesterday. We were given this space W, and we were given a basis for W called x1 and x2. And we noticed that this basis, linearly independent spans, was not orthogonal. That is, the angle between them was not 90 degrees. And so we said, that's a bummer. We want an orthogonal basis, so let's construct one. And so the way we constructed our orthogonal basis was we started with the first vector, and we said the first original vector is going to become the first vector in our new orthogonal basis. Then we constructed our second vector, let's call it v2, and to construct our second vector, we took the second vector we were given, but we subtracted out the part of the second vector that was in line with our first vector. And I don't know if it's okay to derail or to try to put this in an analogy. Like, I don't know if you've ever built anything, but we built a house for my parents, and like we literally had this empty lot, and we're trying to build a house, and we want our house to be square. And I probably elsewhere told you that I'm not very good at making things square, but nevertheless, we're trying to make it square. We've got to figure out where the house goes. Like, there is no coordinate system. There is no, like, the street is far away. There's hills, there's trees. Like, there is nothing that tells us necessarily where to put the house. And so by analogy, you can think about you imagine that we just sort of randomly just draw a couple of lines, and we're like, okay, here's our first line. Maybe I'll call it x1, and here's my second line, x2. Okay. And I'm like, I've got to figure out where I'm going to put this house. Like, how am I going to orient it? And so the x1, x2, those represent my initial basis, my initial frame of reference. And then what we come through is we're like, well, what do we do, Dad? Like, I was building with my dad and my brother. What do you do? I don't know. That first line looks okay. Let's keep that one. And so we keep the first line in place. And so we'll call that one our V1. And then, okay, well, if that's our V1, then, well, why don't you just kick that X2 over a little bit to that side, and that'll make it 90 degrees. Okay. That'll be our second frame of reference. Like, it's like you just start with something and you just adjust it into place so it works. If we'd started with a different, if my X1 had been here, oh, that looks a little too parallel. If my X1 had been here and my X2 had been there, then maybe I would have ended up with this as my V1 and this as my V2. Right? Something along those lines, right? You're just you take the first vector as a starting place, and then you basically kick the other one over so that it's perpendicular. And that kicking process, I mean, that's a little metaphorical, but that kicking process is just this part where we're subtracting out whatever part of the second vector was pointing in the wrong direction. Questions, or ready to do another example? I also have a question in the chat from Dibs. He said, you built a house with just 3 people. So my dad and my brother and I built it, and we actually I think I was in college at the time. My brother was in high school. And we got it all the way to, I think we got it all the way framed to trusses and all that. And then we ran out of time. And so my dad subbed out most of the rest of it. But yeah, it was pretty fun. We had funny story from that. We got the floor. Well, actually a couple of funny stories. We put the floor in place. So it's just a plywood floor, giant empty space. And my brother, we had this friend that was helping us, and she was a cute girl. And so my brother liked her, and he's like, what do we get to do? And my brother is a good dancer. He's just into all kinds of things. He's good at lots of things. And so he convinced my parents that we should hold a swing dance. And so we had this just big old floor space, and I think we got a couple bales of hay or whatever and held a little dance at our new house, just on the floor with a whole bunch of friends and stuff. That was back when you actually could see people face to face. It was an amazing experience. No one wore a mask. Like, you could be closer to 6 feet. Like, you might remember this whole thing from a long time ago. But anyway, a lot of fun times. If you ever get a chance to build something, definitely do it. It's an amazing experience. All right, let's do another example with this same thing. So in example 4, we are going to start with our example x1, x2, and x3. And I want you to notice that x1, x2, and x3 are clearly linearly independent. This word clearly is dangerous, but why can I claim that these are clearly linearly independent? What is it about these vectors that makes that obvious? Okay, so I've got from Felix that they're not scalar multiples, from Abe all the zeros, from Ben they aren't multiples of each other. Yeah, all those things are sort of there, but I don't think they make it clear. There's something that should make it even clearer. From Mahi. That's what I'm after, the pivots. So if you look at this, imagine that we put these things together into a matrix, and you'll see those pivots showing up right there. It's a flip-flopped matrix, but that should make it clear that these are going to be linearly independent. So we have x1, x2, x3. They're clearly linearly independent and thus are a basis for a subspace W of R4. They're not orthogonal. You can see that they aren't orthogonal because imagine if you took the x1 and the x2 and you dotted them with each other, you would get 3. And what's important about 3 in this case? Three is not 0. And for those of you that are trying to do cool typing, like I see people putting this thing in the chat for the not equals, that's cool, it makes sense. But if you want to be totally cool, you do bang equals. That's how you say not equals in programming. So we'll do it either way, but if you want to be all that, you got to exclaim your inequality to the world. So we've got that these are not orthogonal. We want to construct an orthogonal basis. So let's think about how we're going to do it. So we start with our V1, and our V1 is going to be equal to that X1. Right, that's that first vector that we put down. Wow, Ben, what crazy thing do you do to get that character? Are there special characters in Zoom that I'm not aware of? Nice. Copy paste from online. Yeah. I think that every time I ask a question in class that requires a special character, you should Google search to find the right typesetting and then copy paste it over into the chat. That is definitely a good way to use your time in class. So we've got our V1 equals X1. So then our V2, so it's going to, our V2, oh my gosh, Dust. Is going to start with that X2. But these guys might not be, the V2 and the X2 might not be perpendicular to V1. And so we've got to subtract out or get rid of or kick out of the way all of the part of V of X2 that's pointing in the wrong direction. So how much is pointing in the wrong direction? Well, it's the part of X2 that's in line with V1. So it's like you have the green part, and then you're going to get rid of, subtract, all of the part that's going in the wrong direction. Okay. And then our V3 is going to start with the X3. And then we've got to get rid of all of the X3 that's pointing in the wrong direction. Well, now there's 2 directions that could be wrong. It could be wrong, it could be wrong in the V1 direction. It could be wrong in the V2 direction. And so we're going to subtract out X3 dot V1 over V1 dot V1. Come on. Times V1. And we're going to subtract out X3 dot V2 over V2 dot V2, V2. Second time. So we have x3. Maybe and we're going to subtract out. This is a little bit awkward, but I'm going to subtract out kind of the yellowish part that's tied to V1. And I'm going to subtract out the greenish part that's tied to V2. And that'll give me this new V3 part. So again, we're taking x3 and then we're subtracting the part pointing the wrong direction. So it's like the blue part minus the yellow part and the green part. I don't know if that color scheme makes sense. Okay. Questions about the formulas? Okay. So now we just need to do it. So our V1 is going to just be 1, 1, 1, 1. Same as our X1. Our V2 is going to equal X2, which is 0, 1, 1, 1. And then we're going to subtract some fraction times V1, which is 1, 1, 1, 1. So I need to know what that fraction is. So that fraction is going to come from right here. So I've got 3/4 from Mahi, Gerline, and Felix. I got a 3/3 from somebody. I'm seeing lots of 3/4, so I'll go with the 3/4. Okay. So if we do this, what's our final vector? I got it like a minus 3/4, 1/4, 1/4, 1/4. And this is going to be my new greenish vector. And sorry, there's not enough colors in the rainbow to make everything perfectly color coordinated. Question for you before we go on. What's the relationship between V1 and V2 here? Yeah, from Felix and Gerald and Ben and Megumi and Abe and Richard, they are orthogonal, right? The V1 is perpendicular to V2. And what tool do you use to see that so nicely? Like, you can just look at it. So we can use our OT product, our dot product. And so we get -3/4 plus a fourth plus a fourth plus a fourth equals 0. So we can just see that it's working. Sweet. Let's do this one more time. So then if we want to find our V3, we're going to start with our X3, 0, 0, 1, 1. And then we got to subtract out some part of V1, 1, 1, 1, 1. And we got to subtract out some part of V2. Here's one place I want you to be careful. It's easy at this stage. It would be easy to go, is this purple thing a reference to X1 or is it a reference to V1? Because X1 and V1 are the same thing. Okay, so it'd be easy to get confused of what's what. And what I want to remind you of is that it's a reference to the V's, not the X's. They happen to be the same in the first case, but they're not going to be the same in the second case. So we've got 1, 1, 1, 1, and then the -3/4, 1/4, 1/4, 1/4. And there should be a yellow fraction, and then I think we've got a green fraction. So this one's coming from here. I got a 1/2 for the first, I think is what I'm seeing in the chat. And the second one is, I'm seeing 1/6. 1/6. Sixths out there. Is that what you guys are getting? 2/3? Yeah, 1/6 or 2/3. Sorry, I'm just checking my own math. The majority says 2/3. Is that right? Sorry, I'm just checking my notes. Let's just do it. I don't want to second guess it. So x3.v2, 0, 0, 1/4, and 1/4. So I'm going to get half in the numerator, and then v2, v2. So I get a half over 9 plus 1 plus 1, 12 sixteenths. 12 sixteenths. So half over 3/4. Two-thirds? Okay. So we got a 2/3 there. Okay. Questions? So now we need to multiply all this stuff together. I've got this lone random 1/6 out there. Okay, so you multiply all that stuff together, and what you gonna get? You got 0 for the first entry, and then -2/3, and then 1/3 and 1/3. And thank you, Dibs, for that. Again, you can dot them together. So if you take V1 dotted with V3, you should get what, 0 minus 2/3 plus 1/3 plus 1/3, you're going to get 0. And if you take V2 dotted with V3, got 0 minus 2/12 plus 1/12 plus 1/12, also 0. So again, what have we shown? We've shown that we have an orthogonal basis. Is this orthogonal basis unique? So is the basis unique? Yeah, no. It's not unique. And again, remember the picture up here. The basis is not unique. What we did was we found that basis iteratively, like step by step. And so if you change the order of the steps, you would get a different basis. It'll span the space regardless of what order you do it in, but you'll get a different basis. Let's keep moving. So we just did a couple of examples using this Gram-Schmidt process, and this next theorem basically tells you what the process looks like. And you should now see what's going on. So your V1 is X1. Your V2 is going to be, V2 says, start with your X2 and then subtract out all the bad part of X of X2. And that'll give you your new V2. And your V3 says take your new vector X3 and subtract all the bad part that's in line with the yellow one, subtract out all the bad part that's in line with the green one, and that'll give you your V3. And you're going to keep on going where you're like your V4 is going to be, or sorry, your VP would be XP, and then you'll subtract out the part that's in line with the yellow one, and then you'll subtract out the part that's in line with the green one, and then you'll keep on going and going and subtract out the part that's in line with the orange one. Like you'll keep subtracting out all of the bad parts until you're just left with the part that is perpendicular to all those other vectors. So this gives you V1 to VP as an orthogonal basis for W. Where the spans are the same. Notice that this span statement is specifically referring to the K's. Like that's the important part of that lowest statement. That at any point along the way, you could stop at any point and the first vector spans the same, like the first two vectors span the same space. The first three vectors span the same space. The first four vectors in the two sets span the same space, which is kind of cool. So the result of all this is that every non-zero subspace W in Rn has an orthogonal basis. And this is an orthogonal basis. And if you want to find an orthonormal basis, it's easily constructed by first finding the orthogonal basis and then turning everything into unit vectors. So for example, in example 3, we had V1 we found was like 3, 0, -1. This is our V1 that we found. And V2 was -1, 5, -3. And so this is an orthogonal basis. And so we could normalize it. We could change our length. So our orthonormal basis would be, now V was so yesterday, now it's going to be U's. So we'll call it U1. And so our U1 is going to be V1 divided by the length. What's the length of V1? So I've got some square root of 10s out there. So U1 is going to be 1 over root 10 times the V1 vector. And then U2, in addition to being one of the greatest bands of all time, would be something, what's the magnitude of V2? Square root of 35. Thank you, Juan and Tui. And so notice, you might say, well, what are these? This would be 1 divided by the magnitude of V1. 1 divided by the magnitude of V2. So to sum up, what we have done is we've created a system, a method, an iterative process, a step-by-step process called Gram-Schmidt that allows us to take an arbitrary basis and turn it into an orthonormal basis. That is a basis where all the vectors are perpendicular to each other and of length 1.